Okay? There is a possibility. Okay? So if you look at our function, right? I'm going to write out our function from, I'm going to move this graph, this thing away. If we look at our function from B to C, right? We have M as a function of X is equal to minus 25 times 10 to the power 3 X squared plus by 120 times 10 to the power 3x minus by 96 times 10 to the power 3. Okay. And based on this statement, right, when the shear is equal to the shear force is equal to 0. Okay, that's a possibility. So when this is the case, we are going to substitute x is equal to 2.4 into the equation 1. I'm going to call this equation 1. Okay. Why are we doing that? Okay. We know based on this function over here, right, we are going to get a response that is set phase. Right? We need to find where is the turning point or where is the maximum. Right? And we know the maximum is going to be at x is equal to what? 2.4. Why? Because when x crosses, when the shear force is equal to 0 or crosses 0, there is a possibility that your bending moment will be at its what? Maximum. Okay. So now you substitute. So M, when x is equal to 2.4, so this is equal to minus 25 times 10 to the power 3, 2.4 squared, plus by 120 times 10 to the power 3, multiplied by 2.4, minus by 96 times 10 to the power 3. So this will yield minus 25 power 3 times by 2.4 squared, plus by 120 power 3 times by 2.4, minus by 96 power 3 is equal to 48 times 10 to the power 3 Newton meter. Okay. So you know that this will go until 48. Okay. Then the next thing I want to do, I want to take note at 32 what's going to happen first before I sketch. Okay. So I'm going to sketch draw a line at 32 or 3.2. I better not draw a line. Okay. So at 3.2, we know that our shear stress, our bending moment is 32. Okay. So I'm going to put in 32. 32. Okay. Why I do that now, then we can sketch our what? Our curve. We know where the maximum point it is. We know where the starting point is. We know where the ending point is. Okay, so now I'm going to sketch, or we are going to sketch. Okay, so it's going to look like this. Okay, so that is our bending moment diagram up to 3.2. Okay, and then the last one is most easy. We know that point C to point D, we have a linear function, right? And it's going to be a straight line, and at point D, it's going to be 0. So from there to there, it's going to be a straight line. Okay. So that is our shear force and bending moment diagram. Now, I want to explain both there is a trend between both the shear force and bending moment diagram. Okay. So what trend are we talking about? Okay. So if we were to look at the shear force, I'm going to make this statement. Okay. So this is the first trend that we see. Right? When shear force is equal to 0, there is a possibility that bending moment is maximum. So if you look at point 8, right, the shear force is at its very minimum, right? Because it crosses zero. And when it crosses zero, shear force again is at its what? Maximum. That is why the statement is made when shear force is equal to, there is a what? Possibility. You have to what? Check. Are we clear? Most important thing is we have to check. The next trend is this. Okay, I want you to observe this trend. These trends are important because it will help you see whether your sketch is correct or wrong. Okay. The next statement is when shear force diagram magnitude is positive, okay, in bending moment diagram, the gradient is positive also. Okay. So let's see. Okay, what does this statement mean? So we know in this region over here, your bending moment, sorry, your shear force magnitude, they're all what? Positive. Yes or no? So if you look at the gradient from 0.8 to 2.4, right? If you look at the gradients are all what? If you draw the tangent, the gradients are always what? Positive. Can you see that? Right? Positive gradient. Right? So because we have positive magnitude. So likewise, okay, when shear force magnitude is negative, right? Bending moment diagram the grade is negative also. Right? So let's look at the blues. So all these are what? Negative. All these are what? Negative magnitude. So if we look at the gradient, they also come to look like what? Negative. Yes or no? It's coming down, right? It is what? Negative. Okay. So from here, these are the things that you have to remember. Okay. Right. Another thing I want to tell you is, what do we mean by positive bending and what do we mean by negative bending? Okay. So if we look at the deformation pattern, okay, if we look at the deformation pattern, positive bending will induce a sort of smiley face deformation pattern. We're talking about deformation pattern. We're not talking about mathematical equation. Okay? And when there's negative bending moment, the deformation is a set face. Okay? So from here, right, we can more or less sketch how the structure will deform. Okay, so watch this. So you can see over here, that's our beam, right? So the structure based on, I'm doing this based on bending moment diagram. Okay, so I believe the structure will deform as a set face up to here. Then from here, you'll become a smiling face until here. Right? Makes sense, right? Because from 0 to a bit more, not exactly at 0.8, okay? Slightly over 0. You can see the gradient, okay? Slightly over 0.8, right? Then when it cross over, then you get the what? You get the, down here is still sad face, right? Then you have smiling face down here, okay? So from the bending moment diagram, you can sketch the deformation pattern, okay? And does it make sense to you? It's logical, right? Okay. What else do I need to tell you about the shear force and bending moment diagram? Okay, for now, that's all. Okay. So this question asks, right? What is the maximum stress acting on our structure? Okay. So we have to pick points. Now, remember, we are combining shear force and bending moment. Okay. Now, where should we analyze? Okay. So let me tell you. So now we have constructed our shear force and bending moment diagram. Let me copy this whole thing. Let me copy this whole thing. And now we need this. Okay. We like to determine where the maximum, not maximum, where stresses is the most critical to the structure. And we did say last week that failure will occur here. Okay. So we are aware that we have to use two formulas now. Right? We have to use two formulas. We have to use one formula where normal stress X is equal to mz over izz y. Right? We have to use one formula. The next one is we have to use shear stress is equal to Vy over Izz Qz divided by T, and we're going to do thin wall analysis. Agree? Now the question is this, right? What we realize is that what mx or what mz and Vy values to use. Okay. What is the value that you have to use? Okay. So if you look at the shear force and bending moment diagram, it is very frustrating. Yes or no? Why do I say it's frustrating? Let's look at when x is equal to 0.8. Right? When x is equal to 0.8, mz is equal to your Vy is equal to what? The Vy is equal to 80 times 10 to the power 3 Newton, which is the highest. That's why we picked that point. But then, when you look at the moment, it is at minus 16 times 10 to the power 3 Newton meter. Okay. So that's one point, like, we pick it because it has the highest what? Shear force. Then we pick the next one where you have the highest bending moment, where X is equal to 2.4. When X is equal to 2.4, Vy is equal to